Hello my friends, welcome again to my video channel. Today we will start a new project, the Philips function generator PM5127. It is from the late 70s of the last century. It's an analog, of course an analog function generator for sine wave, square and triangle. The duty cycle can be adjusted. It operates from 0.1 Hz, that means 10 millihertz, up to 1 megahertz. Okay, the seller promised that the switch is lit when it is switched on. Other things he couldn't test, he said. On the other hand, I've seen in the background an electronic lab, and if someone is selling such an equipment and saying he cannot test it, I don't believe it. Simply, it means that it is bad, not working. So I paid only some euros for it. Let's have a first check. A first optical inspection shows us that it's in rather good condition. The knobs are all present. The connectors are not damaged as I see. Switches are there, they are moving as they should. Duty cycle and DC offset can be set, amplitude, waveform. Output, we have a sync output, attenuator in 20 dB steps. That's all okay. On the side here's a small damage at the handle, but it doesn't matter. Rear side, the cable can be stored here. This side it's okay. Optically it's good, so let's have a first test of the output signal, whether there's an output signal or not. Let's connect the scope. The first check is the TTL output. Scope is set to 1 milliseconds per division. Frequency is 1 kilohertz times 10, should be 10 kilohertz. When I switch it on, we see a short time signal and then it disappears. No further signal is here. I can switch to any frequency. When I switch it off, I'm in the range now of 10 kilohertz. Let's go to 100 kilohertz. It's always the same picture, so there's something wrong in the frequency generation. As I see, the output is also, as we can see that. The attenuator works. We have a heavy DC signal. The sensitivity is 100 millivolt per division. The DC offset, okay, seems to work, but it's a little bit, should be a sine wave. Interesting. Should be 100 kilohertz. We are far away from 100 kilohertz. Something in the range of 16 kilohertz or so. Cannot be adjusted. Sweep is nothing. Triangle. Square wave. It's 145 Hertz. Should be 10K times 3, 30 kilohertz, 10 kilohertz. No reaction. I'm going to go to other frequencies. We always have the same output frequency. I can vary the DC offset. Okay. What says the duty cycle? Now the signal is gone. Do we have bad contacts? You see, something to do. Let's open it. Here we have the top side. A lot of dust on the contacts. Between the contacts has to be cleaned. It came through the grill here, which is on the top and bottom cover, they are identical. There's also a lot of dust. This looks not so nice. Maybe we have a problem with the contacts, as we have seen during the first test. But there is a problem. Now we clean it. Here we have the bottom side. Looks also very good. This is a very big copper strip. It's for grounding. This is the output here, the output connector. Maybe there's a ground to the output, to the final output. I don't know why, but well, it is as it is. Power transformer. Here we have a big pot for the frequency setting, and you hear the sound. It sounds like a wire wound pot. It's not a carbon pot or metal film pot. It's a wire wound pot. In those days, such wire wound pots were used for good linearity, because carbon pots, even if they are linear, they have the stamp lin on it. Lin dot does not mean that they are strictly linear. They have an error over the whole setting range between 0 and 100%. A wire wound pot doesn't have this error. It is wire wound, and as long as the wire is made, the winding is made correctly with correct spaces, and the wire has a constant thickness, constant diameter, then the resistance per degree movement is correct, and then we have a very linear scale, which cannot be achieved with carbon pots. Metal film pots would also be possible to be used for this purpose, but I think in those days metal film pots were not available or very, very expensive. Such a wire wound pot is cheaper for good linearity. Okay, now let's have a first check. First I will clean it, then we can have a look at the power supply. That's the first check we have to do, and then do further checks if necessary. First thing is to check the power supply. The power supply is rather straightforward. It's a linear power supply. You can't see the details, not necessary. We have your two rectifiers. One output is plus 24 volt and minus 24 volt, and other voltages are plus and minus 15 volt. They are derived with this integrated circuit here. So I first check the voltages behind the rectifiers at the filter caps. This is minus. I have a 10 volt per division, 10, 20, 30, minus 35 volt. And on the other side we should have, plus 10, 20, 30 volt. We have 1 volt per division times 10. So we have more than 30 volt. I prefer using a scope for such a measurement to see whether there's a ripple on it or not, whether the ripple is too high. This indicates me that the ripple is rather low, within a acceptable value, because the output voltage is 24 volt. That's below the ripple. A measurement with a voltmeter wouldn't give me this information, and then we can check the other voltages. Now to measure the stabilized output voltages. I'm measuring here the voltage, and we can see it on the screen also. Here we have plus 24 stabilized. We have 2.3 something, 23 volt measured, okay. Here we have minus 23, 24, and here we should have 14 volt. Should it be 15, 14, 15? What should it be? 1 moment. Where is it? Power supply. 15 volt. The output here 144, 14.4, and here we have minus 15.5. That's okay. The voltages are present, and we see no hum on it. It is stabilized, hum free, no oscillations on it, as it should be. So we can say the power supply is okay. And then we can focus on the next topic. There's a generation of the frequencies. We have seen that the power supply is okay. We have the specified voltages. Now we should focus in the next step on the oscillator. With this section here, we have here the switch capacitors, the resistors, trimmers and so on for the various frequency ranges. These two transistors, I think, are the output transistors. Here we have a sine shaper. In this oscillator we are generating a triangle and square wave. And the triangle here is converted into a sine wave in this section. And this is the output section, the power output amplifier. We have seen that the frequency cannot be varied. It has a rather odd behavior, strange behavior, so I think the problem should be searched now in the oscillator section. I will look for a test point to check what the oscillator does, and then we can continue. Before I can continue my measurements, I had to install a reference ground. That's a problem in many electronic equipment, where to find a reference ground. You may think, okay, use this one. No, this one cannot be used. This one is the chassis. It's connected to the protective earth of the wall outlet. This is not the ground of the electronic. The electronic ground is isolated from the chassis. We can see it here in the drawing. This is the chassis of the housing. It's from the power supply, and the electronic ground is connected via this 100 kilo ohm resistor and this 4.7 nanofarad to the chassis ground. So this cannot be used. We need this one. And the problem is where to find on this board a reference ground. Okay, you can look for some components where you say, for example, this electrolytic capacitor, the minus could be ground. It's wrong, it's a plus one here. Here was a ground for me for the measurement of the power supply, that's okay. But when I want to measure here, the distance is too long for the probe. So I drilled a hole in it, 3 mm, and connected it to the electronic ground. Here's the electronic ground, this copper strip which goes to the output amplifier. This is the output, the BNC connector, and here we see the chassis ground, and this is a 100 kilo ohm resistor and the capacitor, 4.7 nanofarad in parallel. Again, the chassis is not the electronic ground. The electronic ground is here, and now we have a reference on top of the board. The lug is connected via this black cable to the electronic ground. The probe is connected to the output of the oscillator part. Here at the emitter and the collector of these two transistors. Here we have the output, which is switched via the mode switch to the sine converter, sine shaper, or to the square wave generator, or it is connected directly to the output, to the power transistor of the output stage. What we see is not nice. It's very unstable, very touchy. The set frequency is 50 kilohertz. It does not react on the scale. We have 2 milliseconds per division, so we have approximately 10 milliseconds plus minus. When I touch the switch, nothing happens. It's also good. When it is switched off, nothing happens. Something happens. Well, we see that obviously the switches all need cleaning. When I switch to the duty cycle, when I go back, this is all very touchy. Maybe we have also problems with the board itself, bad solder connections. Anyhow, I will remove the faceplate and clean the switches first. The best position is this upright position. Then we can soak the switches at this point with the contact cleaner. It's the only way to get it, because here there are no holes, but along this lever here it is possible to bring it in to prevent coming out and making some dirt on the board, which is not nice. We have to add some paper to soak it up. Well, let's start. and so on and so on. Next step is to do a test of the switches. All knobs are out, so always the first and second one has to be connected. Okay, correct, 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 correct. Counter check, no connection. And then next step is press it in. Then we have contact from here to here. From here to here, here to here, and here to here. Same we have. Sorry, must switch on off, of course. Oops, first, then contact, contact. So I will check all these switches this way. I remove the paper, feed in a new one, and then I use a contact wash to spray out the old contact cleaner and the residues. It's stated in the description of the contact cleaner that it should be washed out. What I'm doing now, same procedure. Same procedure, and so on and so on. And now seems that we have success. The front panel is in place again. It is cleaned. I installed all the knobs. The end caps are not installed up to now. Maybe I have to readjust the knobs. The mechanical center setting. Also for the scale. Range times 1 kilo. 10 kilohertz. We have 10 point something. And here we have 1 kilohertz. 1.2. Maybe I have to readjust this knob or the scale or internally the pots. Let's go to times 1. This is 10 Hertz. We have 10 Hertz. Go down to 5 Hertz. 5.3. We also have a little bit too much. I think the knob has to be readjusted. This is 1 Hertz. Also okay. Times 10. It's 10 Hertz. A little bit more. Should be 100. 103 times 100. It's 1 kilohertz. Down to 100 Hertz. I'm still at the output of the oscillator. I cannot switch the waveform. I will check it in the next step. 1 kilohertz. 10 kilohertz. 100 kilohertz. Down to 1 kilohertz, and this is 100 kilohertz up to 1 megahertz. Well, this seems to be okay. Frequency can be fine adjusted with this knob. That's also okay. Things like duty cycle. Yes. Even the megahertz signal can be changed with a duty cycle. The offset is only valid for the output here. And now I will connect the scope to the output and see whether the waveforms are okay. The scope is now connected to the output. It's a 50 ohm cable. It's not terminated with 50 ohms here. So we'll have a problem with the square wave, but in general, same topic. When I go to 0 dB, I can adjust the amplitude. It is a sine wave. This is a triangle function we had before with the... I see here something not okay, but it's in the megahertz position. Let's go to kilohertz. Maybe the signal is a little bit distorted in the megahertz range. It looks better. Sine wave, triangle, and square wave. 6, let's go to 5 kilohertz. Well, next step is the DC offset. The trigger is not okay. but the DC offset is okay, only in case that there is no DC offset set. One of the pots has to be readjusted. Duty cycle, okay, between 10% and 90%. It's also okay. The output attenuator works. It is 40 dB. And minus 60 dB. I should go to auto trigger. Okay, it's also good. That's it. Seems everything is okay now. And we can start with the alignment. But we have success. It was only a set of dirty switches, dirty contacts. Seems that this unit wasn't used for many years. It was stored as it looks anywhere else, and then someone found it and said, okay, I can sell it and make some money. It's okay for me. Now the little generator is running again. In the next video sequence, the next video, we will do the alignment, complete alignment. I think it's a rather challenging project because there are a lot of pots and the frequency has to be set and the mode and so on. But this day or this evening ends with a result. This is the end of part 1 of the videos about the Philips PM5127, about this function generator. In part 2 we will do the alignment, complete alignment, and maybe some further checks or tests. Stay healthy, stay tuned, and see you on this channel.